Hello students, today we will discuss hereditary and topological property of regular space. Till now we have discussed hereditary and topological property of T0 space, T1 space, T2 space. In T0 space we take two distinct points, and for these distinct points we have an open set. One point belongs to this, another point does not belong to this. And in case of T1 space, for two distinct points S and Y, we have two open sets. They may be disjoint and they may not be disjoint. One point belongs to this set, another point belongs to this set. And in case of this T2, we have for two distinct points, we have two disjoint open set. We have two disjoint open set, and this open disjoint open set. One point belongs to this, another point belongs to this. Now here we observe that for two distinct points we have one open set. For two distinct points we have two open sets. They may be disjoint, they may not be disjoint. And for two distinct points we have two disjoint open sets. That is, points are separated by open sets. Now in regular space we have a closed set and a point which does not belong to that. And now we find two disjoint open set. One belongs to this and another closed set is contained in another disjoint open set, such that G intersection H is empty. Here we will separate a point and a closed set with two disjoint open set. Now we look on a definition of regular space. Let Xt be a topological space and B be a closed subset, be a closed subset of X. Let X be a point from X such that X does not belong to B. Xt be a topological space, B be a closed subset of X, and X belong to X such that X does not belong to X. Now we find two disjoint open set. Now we find two disjoint open sets G and H such that X belongs to G and B is contained in H. Where G and H are disjoint. That property is said to be, that space is said to be regular space. Now we have given a topological space, B be a closed subset of X, a point which does not belong to this B closed subset. Then if you are able to find two disjoint open set such that one point belongs to open set and another closed set belong to another open set, and both G and H are disjoint, that space is said to be regular space. Now we do some example of regular space. Examples. First of all, let X be set which consists two elements 0 and 1, and T be a topology defined on these two elements, and this is this phi 0 and X. That this topology forms a regular space, and this topology has a special name, and that name is Sierpinski topology. Pinsky topology. Now we take another example, Michael plane topology. Michael, M-I-C-H-A, Michael line topology. Michael line topology. In this case, in Michael line, let HB is set real line, and the topology T here is of the type open set element. A and B open interval, you can say, such that A and B are rationals. A and B belong to Q union X, where X belongs to R minus Q. This type of topology is called as Michael line. Michael, M-I-C-H-A-E-L, Michael line topology. This is also form, you can check easily, this type of topology also form a regular space. Now we take another example of indiscrete metric space, indiscrete topological space. Let X be an infinite set, and the topology is indiscrete. Then this topology is also a regular space, form a regular space. Now we come to hereditary property of the regular space. Before that, we take definition in brief. Let Xt be a topological space, B be a closed subset of X, a point X does not belong to B. Then we have two open set disjoint in fact such that X belongs to G and B is containing H, and G intersection H is disjoint. Then that space is said to be regular space. Now here the property being a regular space is a hereditary property. Or in other words, you can say subspace of a regular space is again a regular space. Now see the proof of this. Let Xt be a topological space, and Y a subset of X be a subspace of X. Now we saw that Y T star, where T star is the relative topology with respect to the set X. Now we saw that Y T star or Y is a regular space. Now we saw that Y is a regular space. For this we take a closed subset, say B star of Y. Here Y is a subspace, or we can denote the subspace Y by Y T star. The element, the open set of the subspace Y is of the form Y intersection G, where G belongs to T. G belongs to T, where T is topology defined on X. So you note that here the elements of relative topology, elements of the subspace Y is of the form this Y intersection G, where G belongs to T. Now the closed subset B star of Y will be of the form B star is equal to B intersection Y, where B belongs to topology, where B is a closed subset of Xt topology. Now we take an element y which does not belongs to B star. Now we construct here two open set which one belongs to y belongs to one open set, and this closed set is contained in another open set, and though these both open sets are disjoint. For this, now y does not belong to B star means B star is equal to B intersection y. This implies y does not belongs to B intersection y, but y belongs to y. So this implies y does not belongs to B, but y is a subset of x, so y also belongs to x. Now we observe that y is the element of x, b is a closed subset of x, and y does not belong to b. So it is given xt is a regular space. Xt is a regular space. Here we note that B is a closed subset of X and Y is an element. Y is an element which does not belong to B. So by definition of regularity of space X, we can find two disjoint open set, say G and H, such that Y belong to G and B is contained in H, provided G intersection H is empty. Now we find two open set in topology XT. Now we have to construct two disjoint open set in the related topology, that in the subspace Y. How? We know Y belongs to G, Y belongs to Y. This implies Y belongs to G intersection Y, and B is contained in H. This implies B intersection Y is also contained in H intersection Y. From here we observe that this is closed set in related topology Y, and we have denoted it by B star, and this is contained in H intersection Y. Here H is open in X and H intersection Y is an open set in topology YT star, or you can say in the related topology, and we denote it by H star. So this implies B star is contained in H star and Y belong to G intersection Y, we denote it by G star. Now for the element Y we find an open set G star. For the closed set B star we find an open set H star such that both are disjoint, and the disjoint can be seen from here. H intersection G star, this is equal to H intersection Y intersection G intersection Y, and G intersection H intersection Y, and this G intersection H we have already taken that they are disjoint phi intersection Y, and this is phi. Thus we conclude that for closed set B star and the element Y does not belong to B star, we find two disjoint open set G star and S star such that Y belong to G star and B star is contained in H star such that G star intersection H star are disjoint, and G star is of the type G intersection Y, and G belong to T, and H star is of the type H intersection Y, H belong to T. Hence we have proved for a closed set B star which is in YT star topology and element does not belong to star, we find two disjoint open set G star and star which hold this condition. Hence we say Xt, a subspace of a regular space, is regular. Now we come to topological property of regular space. Topological property of regular space. In other words, you can say homomorphic image of a regular space is regular. Now, theorem, let the property being a regular space is a topological property. So we can say homomorphic image of a regular space is regular. Proof. Let Xt and Yty, you can say Xt and Yty be two topological spaces, and at be homeomorphism from Xt to Yty topological space. Now we saw if Xt is regular space, then its homomorphic image Yty is also regular. Proof. Let, or you can say be homeomorphism from a topological space Xt to Yty. Here Xt is a regular space. Now we saw that its homomorphic image Y is equal to Fx is also a regular space. Now what we have to do? We take a closed subset of this topology and an element of Y that does not belong to this, and we have to find two disjoint open set from which one this point belong, and that set is contained in that. That is, let B be a closed set in y dy, and y be a point which belong to y such that y does not belongs to b. Since f is homomorphism, you know homomorphism, a map which is bijective and bicontinuous is homomorphism, or you can say map which is bijective and f inverse is continuous is also known as homomorphism. Since f is homomorphism and we have a point y in this y, so we can find an element x belong to x such that y is equal to fx due to homomorphism. Now where x belongs to x, for now y is equal to fx, so fx does not belong to b, but f is homomorphism, so we can further write due to homomorphism x does not belongs to f inverse b. This is due to homomorphism. Now b is a closed set in y and f is a homomorphism. Inverse image of a closed set is closed, so f inverse b is closed in x, and x is also a point of x, so f inverse b is closed in x. X does not belong to f inverse b, and we have given xt is regular. Xt is regular, so f inverse b is closed in this, and x does not belong to this, x is a point of this, so we can find two disjoint open sets such that x belong to G and f inverse b is contained in H and G intersection H are disjoint. Further, f is homomorphism, so fx belong to G, belong to fg, and b is contained in f of h. F is homomorphism, so fx is equal to y, this belong to fg, and f is contained in f of h. You know G and H are open in, we have given homomorphism from x to y. These G and H are open in x. Due to homomorphism, Fg and Fh are open in y. Or that by the definition of homomorphism, directly you can say Fg and Fh are open in y, and Fg intersection f of h, this can be written as due to homomorphism Fg intersection h, and Fg, they are G intersection h is already disjoint, and that. Hence we have find two open set, in fact disjoint open set Fg and Fh for y does not belong to B, such that y belong to that and B is contained in that, and this is a definition of regular space. Hence topological property holds in regular space.
Thanks for watching.